Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over overvoltage and what that is, and I'm going to be using the electrolysis of aqueous sodium chloride to do that. So let's get into this. So first, what is overvoltage? Well, simply put, overvoltage is basically the additional amount of voltage that you have to apply in order to make some non-spontaneous reactions to occur. So you have your typical your expected values of your electrode potentials, but then you may need more than that, and that extra is called the overvoltage. So let's talk about the electrolysis of sodium chloride, an aqueous solution of sodium chloride. So as I said in my other videos, when you have an aqueous solution of sodium chloride and you're trying to figure out or predict what reactions are going to happen at the anode or the cathode, then you have to also take in consideration the fact that water is there, and that also is a contender for a reduction or oxidation reaction at either electrode. So here we have sodium chloride aqueous. So we have, for the oxidation, we have two competing possibilities. We have the oxidation of the chloride ion into chlorine gas, and we have the oxidation of water into oxygen gas. So which one of those is going to be the one that occurs at the anode? And so, as I said before, so with regard to the electrode potentials, you want to compare at the anode. You want oxidation to occur, so the electrons you want them to leave, and that's going to occur most easily with the more negative electrode potential. So here we have the less positive. So you can think of either more negative or less positive. So here we have less positive electrode potential for the water oxidation versus the 1.36 voltage that we have for chlorine. So we would expect at the anode there would be the oxidation of water, and so the production of oxygen gas would occur at the anode. What about the reduction? So again, we have two possible competing reactions that would happen at the cathode for reduction. So we have the sodium ion that could pick up two electrons to become sodium metal, and we also again have water as a competitor. So water could be reduced, pick up two electrons, and that could form hydrogen gas at the cathode. And so we can figure out, well, which one is going to happen at the cathode. Here, we want the more positive one. Remember, so the more positive electrode potential is going to attract the electrons more, and it's going to be more easily reduced. So here we have a negative 2.71, and here we have a negative 0.41. And so here we can see that we have a less negative or a more positive electrode potential compared to here. So again, we would then predict that water would be reduced at the cathode. So here it seems like at first look, you would expect water to be oxidized at the anode and water to be reduced at the cathode. So at the anode, you would be producing oxygen gas, and at the cathode, you'd be producing hydrogen gas, and so that's what you would expect. However, there is an overvoltage. There's an additional voltage that is needed in order to actually reduce or oxidize water. So what we actually find is at the cathode, you actually do produce hydrogen gas at the cathode like you would expect. But in actuality, when you run this experiment, you would produce chlorine gas instead of oxygen gas. And the reason for that is because of the overvoltage for the oxidation of water. You actually need more voltage than you would expect. So here, I just want to point out that we're looking at the non-standard non-standard conditions for water. So typically when you're dealing with water, your OH minus concentration is going to be 1 times 10 to the negative 7 molar for your typical water, right? Because you have the auto ionization of water, and so that leads to 1 times 10 to the 7 molar of your hydroxide ion, and then also 1 times 10 to the negative 7 molar for your H plus ion. So under these conditions, the non-standard electrode potential is negative 0.41 volts for the reduction and 0.82 volts for the oxidation. So for the oxidation, if we know that typically what the overvoltage of water is going to be is between 0.4 and 0.6 extra voltage, if you hit that with, say, let's say 0.6, if we add a point, well, let's say 0.4. So if we add 0.4 to this, then that becomes a 1.22 voltage. That would be less than the positive 1.36, right? Um, so in that case, your voltage, your electrode potential for the chlorine is more positive. And so again, in this case, if it was just 1.22, water would be oxidized at the electrode. But if we go to 0.6, if we add 0.6 to this, that'd be 1.42. So 1.42 would be necessary for the oxidation of water at the anode. So in this case, if the overvoltage is 0.6, then that's what you would need to add. That would be the extra voltage you would need to add in order to actually get the oxidation of water. So without that overvoltage, the water oxidation of water would not happen, and you get chlorine production instead. So you get the oxidation of the chloride ion instead. So that's something you would need to keep in mind when you're thinking about these sorts of reactions. So the oxidation of water or the reduction of water could have an overvoltage along with it, so it may not occur unless you add that additional voltage. Now, whether you get chlorine gas to form or oxygen gas to form at the anode in an actual experiment, that's going to depend on several things. So that I won't get into, but overvoltage is something you want to kind of keep in mind when you're thinking through these sorts of problems when you're talking about the electrolysis of aqueous solutions. So I hope this was helpful. If you enjoyed this video, if you like this video, but then please, by all means, share, like the video, hit that notification bell right there. And also subscribe to my channel. Hit that notification bell right up there. Also, make sure you hit the all, click all after you hit the notification bell, so that way you can be notified by all the videos that I put out. Also, put a comment down in the comment section. Let me know what you think. Ask me questions. I'd love to hear from you. Thanks for joining me. Have a great day.